Firewall Paradox. The Firewall Paradox is a significant puzzle in science related to black holes. It presents a very strange idea. Instead of being smooth and calm at the edge of a black hole, called the event horizon, there might actually be a wall of intense energy known as a firewall. If this concept is true, then anything falling into a black hole would be incinerated right at the event horizon. This idea causes a major conflict in physics. Einstein's theory of general relativity claims that falling into a black hole should feel smooth and uneventful initially, with nothing unusual occurring at the event horizon. But the firewall hypothesis suggests the complete opposite. It predicts a violent, fiery boundary. Since both theories contradict each other, scientists are left with a paradox. How do black holes actually function? To understand the firewall paradox, we first need to examine how black holes are supposed to work based on Einstein's general relativity. A black hole is a region in space where gravity is so powerful that nothing, not even light, can escape its pull. The event horizon is the boundary of the black hole, the point of no return, where anything crossing it becomes permanently trapped. According to Einstein's theory, falling through the event horizon should feel completely normal. This idea is based on a principle called the equivalence principle, which states that the laws of physics should appear the same to all observers, no matter where they are or how fast they are moving. Based on this, crossing the event horizon should not cause any sudden or dramatic experiences. However, once we factor in quantum mechanics, the set of rules governing tiny particles, things become more complex. So, what exactly is a firewall? The firewall hypothesis argues that instead of a smooth event horizon, there is a blazing wall of energy surrounding the black hole. This immense energy comes from a breakdown in the quantum entanglement between particles inside the black hole and the particles in the radiation emitted from it, known as Hawking radiation. Hawking radiation is a result of quantum effects occurring near the event horizon. Over time, this radiation causes a black hole to lose mass and eventually vanish. According to quantum mechanics, information about everything that falls into a black hole must somehow escape in this radiation. But for that to happen, the quantum entanglement must be broken. When that happens, it releases a massive amount of energy, resulting in the creation of a firewall. If firewalls are real, they would obliterate anything attempting to cross the event horizon. This contradicts general relativity's prediction of a smooth and calm transition, leading to a serious clash between two of the most powerful theories in physics. Why does this matter? The firewall paradox is important because it highlights a major problem in our understanding of the universe. Quantum mechanics and general relativity are two of the most successful scientific frameworks ever developed. Yet the paradox reveals they don't agree when it comes to black holes. This disagreement suggests that at least one of these theories is incomplete, or that we are missing a deeper explanation capable of reconciling the two. The paradox also brings into question our very understanding of space-time, the fabric of the universe. If firewalls do exist, then space-time might not be smooth and continuous near a black hole, as general relativity implies. Instead, it could break down under extreme conditions, raising deeper questions about the nature of the universe at its most fundamental level. Ideas to solve the paradox. Scientists have proposed several ideas to resolve the firewall paradox, but none have been definitively proven. Here are the main theories. Firewalls are real. Some physicists argue that firewalls must exist to preserve the rules of quantum mechanics. If true, this would mean we need to revise general relativity and accept that the event horizon is not smooth. Information escapes without firewalls. Others believe that black holes can preserve information in Hawking radiation without the need for firewalls. This would require entirely new explanations for how information is stored and transmitted through the radiation, while still maintaining a smooth event horizon. Complementarity. This theory suggests the paradox exists because we are interpreting black holes incorrectly. From an external point of view, it appears that information escapes via Hawking radiation. But for someone falling into the black hole, the event horizon seems smooth, and they experience no firewall. Both perspectives are valid, but they can't be observed simultaneously. This concept comes from string theory and aims to bridge quantum mechanics and general relativity. New physics. Some scientists believe the paradox indicates a need for a new theory that unifies quantum mechanics and general relativity, often referred to as quantum gravity. Such a theory could potentially solve the paradox and offer deeper insight into how black holes function. What does the firewall paradox teach us? The firewall paradox isn't just a problem about black holes. It challenges our basic ideas about the universe. It forces scientists to consider the possibility that even our most trusted theories are incomplete. This paradox also reveals that black holes aren't just mysterious cosmic phenomena. They are keys to answering some of the biggest questions in physics. By studying black holes and the paradoxes they present, we're learning not just about gravity or quantum mechanics, but about the true nature of reality. In the end, the firewall paradox reminds us of the limits of human understanding and the sheer complexity of the cosmos. It's a humbling sign of how much we still have to discover. Solving this mystery could lead to revolutionary breakthroughs in our understanding of spacetime, gravity, and the quantum world, bringing us closer to a complete picture of how the universe works. Reversible versus irreversible black hole growth. Irreversible black hole growth. Black holes are among the most mysterious objects in the cosmos. They expand by drawing in matter and energy, increasing in size and mass as they consume their environment. At first glance, this growth seems simple. Once matter moves beyond the event horizon, the edge of the black hole, it is trapped forever. But is this process completely irreversible? Or might there be situations in which a black hole's expansion could, in some manner, be reversed? This inquiry delves into the nature of black holes and the forces that control them, weaving together ideas from thermodynamics, quantum mechanics, and general relativity. How black holes expand. Whenever a black hole absorbs matter or energy, its mass goes up, and the size of its event horizon also increases. The event horizon is directly related to the black hole's mass, which makes its growth both measurable and predictable. This expansion occurs through several mechanisms: accretion of matter, gas, stars, or any other material spiraling inward increases the black hole's mass. Mergers with other black holes. When two black holes collide, they combine their mass to form a larger single black hole, absorbing energy. Even radiation, such as photons, can be absorbed and contribute to a black hole's growth. These processes follow the rules set by Einstein's general relativity, which explains how spacetime bends around a black hole as it gains mass. Once matter has crossed the event horizon, it becomes disconnected from the observable universe, making this growth appear entirely irreversible. The question of reversibility. At the surface level, black hole growth looks irreversible. The event horizon behaves like a one-way door. Anything that enters cannot escape. However, looking deeper reveals more complexity. In this context, Reversibility doesn't necessarily mean the black hole shrinks or literally undoes its growth. Instead, it involves exploring whether some dynamics might allow for the escape of energy or information, essentially reversing the effects of growth. A thermodynamic angle. Black holes follow the principles of thermodynamics. Their surface area is proportional to their entropy, which is a measure of disorder. The second law of thermodynamics states that entropy in an isolated system always increases, implying that black hole growth moves in only one direction. However, there is a twist: Hawking radiation. This phenomenon allows black holes to emit energy and slowly lose mass, raising questions about whether growth is as irreversible as it seems. Hawking radiation as reversal. Over unimaginable timescales, black holes may shrink due to Hawking radiation, slowly decreasing in mass and reducing their event horizon. Although this doesn't bring back the original material that was absorbed, it represents a form of reversal, as the effects of growth are gradually undone. Quantum factors. Quantum mechanics suggests that information swallowed by a black hole might not be lost permanently. Some theories suggest mechanisms by which this information could be released back into the universe, partially reversing the outcomes of black hole growth. The black hole information paradox. If it turns out that data about matter falling into a black hole is released through Hawking radiation, then this would imply that part of the black hole's growth, specifically its rise in entropy, is not truly irreversible. Reversibility in dynamic systems. The surroundings of a black hole can also affect whether its growth is completely one way. For instance, superradiance is a process where black holes shed energy by interacting with particular types of waves or fields. In such scenarios, energy is extracted from the black hole, causing a slight but real reduction in its spin or mass. Tidal disruption events. These usually cause black holes to gain mass, but the energy and angular momentum distribution during such events may challenge the idea that growth is always simple or irreversible. Speculative possibilities. Some theoretical frameworks propose that black holes could behave in ways that simulate reversibility. Wormholes and exotic physics. If black holes are linked to other regions of spacetime, as in wormhole models, then it may be possible for matter or information to exit, partially reversing some effects of growth. Black hole bounce. Some speculative ideas, like those from loop quantum gravity, suggest that black holes could change state or even bounce, returning some matter or energy back to the universe. Irreversibility in reality. Despite all these theoretical discussions, the bulk of evidence indicates that black hole growth is practically irreversible. Matter that crosses the event horizon is gone from the visible universe. Any reversal mechanisms, like Hawking radiation, are either incredibly slow or purely speculative. In everyday terms, the expansion of a black hole is effectively a one-way process. Broader consequences. The concept of reversibility in black holes extends beyond just their behavior. It challenges fundamental ideas about time, entropy, and causality. Entropy and time's arrow. Black hole growth reflects the thermodynamic arrow of time, reinforcing the idea that many physical processes move in a single direction. Unifying physics. Resolving the clash between quantum mechanics and general relativity in the context of black hole behavior could deepen our understanding of the universe. Black holes grow by absorbing matter and energy, and from most viewpoints, this appears irreversible. Yet, quantum mechanics and advanced theoretical frameworks hint that certain elements of this process might be reversed under specific conditions, whether through Hawking radiation, quantum information theories, or exotic physics. The possibility of reversibility invites us to reconsider what we think we know about black holes and the fundamental laws of the cosmos. The Singularity Paradox. The Singularity Paradox stands as one of the greatest enigmas in modern science. It centers around an unusual phenomenon known as a singularity, a bizarre point located at the heart of a black hole where the known laws of physics cease to operate as expected. At this singularity, gravity becomes infinitely strong, and the fabric of space and time appears to lose all meaning. Researchers continue to struggle with how such a condition can logically exist, making it one of the most challenging puzzles in trying to comprehend the cosmos. Defining a singularity. A singularity takes shape when a massive star comes to the end of its life cycle. Stars generate energy by burning fuel within their cores. But once that fuel is exhausted, the star collapses due to its own gravitational force. If the star is sufficiently massive, this collapse produces a black hole. All of the matter from the star gets compressed into an extremely tiny point, one with infinite density and no volume. This is the singularity. The gravitational force at this point is so intense that even light cannot escape, which is why black holes appear completely black. Here's the issue. Infinite density and zero volume are not physically meaningful. They cannot be measured or observed within the real world. These so-called infinities point to the fact that our current models of physics are not yet complete. The clash of two major theories. The Singularity Paradox illustrates a direct conflict between two foundational pillars of physics. General relativity, Einstein's groundbreaking theory of gravity, which explains how massive objects like stars and black holes influence the structure of space and time. General relativity predicts that singularities are an inevitable result of extreme gravitational collapse. According to this framework, space and time effectively end at the singularity. Quantum mechanics. This theory governs the behavior of incredibly small particles like atoms. It operates on probabilities and patterns, but fails when faced with the infinities of a singularity. Because singularities involve both immense gravitational forces and minuscule scales, they expose a breakdown in both theories. Neither general relativity nor quantum mechanics alone can fully explain what occurs within a singularity. It becomes a frontier beyond which our understanding falters. Why the singularity paradox matters. This paradox isn't just confined to black holes. It threatens the foundation of all physical understanding. If singularities are real, they defy the concept that the universe operates according to consistent physical laws. How can an entity exist that violates the very rules that are thought to govern reality? Alternatively, if singularities aren't real, then what actually resides at the center of a black hole? Moreover, the singularity paradox also ties into the Big Bang, the event believed to have sparked the creation of the universe. The Big Bang theory posits that the universe began from a similarly dense and tiny state, essentially, a singularity. By studying singularities in black holes, scientists hope to uncover clues about the origins of the universe itself. Ideas proposed to resolve the singularity paradox. To tackle this paradox, scientists have put forward a number of ideas, each one involving a departure from current physical theories. Quantum gravity. Many physicists believe that a new theory that merges general relativity and quantum mechanics, called quantum gravity, will ultimately resolve the paradox. This unified theory may reveal that singularities are not truly infinite, but represent a type of state that we don't yet comprehend. String theory, a leading contender for quantum gravity. String theory proposes that the universe's smallest components aren't point-like particles, but tiny vibrating strings. These strings have finite size, which could eliminate the infinities predicted by singularities. and instead set a minimum scale for matter and energy. Loop quantum gravity. Another possibility is loop quantum gravity, which posits that space and time are not continuous, but made up of tiny, discrete units. If space-time is granular, then it may prevent the formation of singularities. Instead of collapsing into a point of infinite density, matter might reach a minimal size and then undergo a quantum bounce, reversing the collapse. Cosmic censorship hypothesis. Some theorists suggest that singularities are always concealed behind the event horizon of a black hole, rendering them invisible and irrelevant to the outside universe. This concept, known as the cosmic censorship hypothesis, proposes that singularities are more of a mathematical construct than something that physically exists. Exotic states of matter. Other theories argue that singularities may not form at all. Rather, the intense conditions inside a black hole might give rise to exotic states of matter. This matter could create an extremely dense core that avoids the infinite values predicted by general relativity, offering a more plausible model for the black hole's interior. What we can learn from the Singularity Paradox. The Singularity Paradox is more than just a difficult riddle. It's an opportunity to explore the boundaries of human knowledge. It highlights that our current grasp of physics is incomplete and that we need entirely new frameworks to describe the universe's most extreme environments. The paradox also showcases the deep interconnection between different areas of physics. General relativity excels at explaining large-scale objects like stars and galaxies, while quantum mechanics focuses on the micro-world of particles. Singularities sit at the intersection of these two realms, demanding that they be unified into a single, cohesive theory. Ultimately, the paradox raises profound questions about the nature of existence. What happens to space and time at the singularity? Are there limits to what we can know about reality? By investigating these questions, we may edge closer to uncovering the deepest truths of our universe. The Time Dilation Paradox. The Time Dilation Paradox is a captivating puzzle rooted in how time behaves near a black hole. It's built upon a strange but real concept. Time doesn't pass the same for everyone. When someone falls into a black hole, their sense of time is drastically different from what an observer far away would witness. For the person falling in, time feels normal, but to a distant onlooker, the falling individual appears to slow down, freeze in place, and never completely vanish. This bizarre contrast challenges our fundamental understanding of how time works in the real world. What is time dilation? Time dilation refers to the phenomenon where time flows at varying speeds depending on your location or how fast you're moving. According to Einstein's general theory of relativity, massive bodies like black holes distort the fabric of spacetime, and this distortion slows down time in regions close to the mass. The stronger the gravitational field, the slower time progresses. Black holes push this to the extreme. Their gravity is so intense that, near them, time almost halts entirely compared to areas farther away. At the event horizon, the boundary of a black hole, this effect becomes so powerful that, from an outside observer's point of view, time seems to stop. The paradox. Two perspectives of time. The time dilation paradox arises because two people, one falling into the black hole and one observing from afar, experience time differently. The falling observer. To the individual plunging into the black hole, nothing seems out of the ordinary. Time feels normal. They pass through the event horizon without noticing anything unusual and eventually arrive at the center, the singularity, where gravity is infinitely strong. The distant observer. For someone watching from far away, the picture is vastly different. As the falling person nears the event horizon, they appear to slow down more and more. From this viewpoint, the falling person never actually crosses the event horizon. Instead, their image stretches out, dims, and gradually fades due to the black hole's gravitational effects. This creates the paradox. From the viewpoint of the person falling, they enter the black hole and reach the singularity. But from the outside, it seems they never truly cross the threshold. So, who's right? Einstein's relativity says both perspectives are valid within their own frames of reference. Because time and space behave differently depending on where you are, both experiences can be true at once. Why this matters? The time dilation paradox is important because it exposes how bizarre time really is and forces us to rethink assumptions we usually take for granted. Time is not absolute. Most people assume time ticks at a uniform pace for everyone, everywhere. But this paradox proves otherwise. Time is flexible. It's shaped by gravity and your position in space. Black holes and growth. If objects seem never to cross the event horizon from an external view, then how do black holes grow? Scientists are certain that black holes do gain mass, but the paradox raises questions about the mechanics of matter and energy entering them. The nature of reality. This paradox shows that reality can differ depending on perspective. Two individuals can observe the same event in wildly different ways, and both observations can be true. While strange, this idea is central to Einstein's theory. Real-world relevance. Time dilation isn't limited to black holes. It's something we observe in daily life. For instance, GPS satellites orbiting Earth experience slightly weaker gravity than we do on the surface. As a result, their clocks tick a bit faster, and scientists must correct for this to ensure GPS accuracy. Possible explanations for the paradox. Scientists have proposed various ideas to explain the time dilation paradox. Here are some of the most intriguing. Relative observers. The simplest explanation is that both observers are correct within their own frames. Time and space behave differently based on location, and these differences don't contradict. They simply reflect the weirdness of spacetime. Black hole growth. Even though an outside observer sees the falling object slow down infinitely, black holes are observed to grow. This implies that mass and energy are still absorbed, even if the process isn't visually apparent. Hawking radiation. This radiation, predicted by Stephen Hawking, slowly causes black holes to lose mass and eventually vanish. It adds complexity to the paradox. If matter seems frozen at the event horizon, how can the black hole lose mass over time? This remains an open question in theoretical physics. Quantum mechanics. Some scientists believe that quantum physics might hold the key to resolving the paradox. For instance, quantum effects might allow the information about the falling object to be preserved on the event horizon, even as the object itself continues inward. The holographic principle. This idea suggests that all the information about a falling object is stored on the surface of the event horizon, in two dimensions. To an outside observer, the object is spread thin across the horizon, but for the falling person, they continue deeper into the black hole. This duality may help reconcile both viewpoints. What we learn from the paradox. The time dilation paradox offers profound insights into the nature of the universe. Time and space are interconnected. Time doesn't simply tick along like a metronome. It's deeply tied to the structure of space and to gravity. Massive objects like black holes stretch time in ways that can seem counterintuitive. Perspective is fundamental. In relativity, What one observer sees can be completely different from another's experience, and both are right. This forces us to reconsider the meaning of objective reality, black holes, and beyond. This paradox invites us to explore deeper questions about gravity, spacetime, and the workings of black holes. Solving it could lead to major advances in physics. Everyday impacts. Time dilation isn't just abstract theory, it has real consequences in technology. Systems like GPS depend on our understanding of how gravity alters time. Studying extreme cases like black holes helps fine-tune our grasp of these effects. The time dilation paradox isn't just a strange thought experiment. It's a powerful lens into the flexible, mind-bending behavior of time, gravity, and the cosmos itself. By digging into this paradox, we don't just learn about black holes, we uncover the truly unexpected nature of reality.